Okay, this is lecture 10. We're going to talk about continuity. And I want to remind you of something, okay? I want you to remember this. Okay. The limit of f of x as x approaches a, or I think at this point, I'll say c. Oh, it's just a variable. It doesn't matter, right? What letter we use. Okay. Does not necessarily have any relationship to f of c. Okay. However, it is sometimes the case that the limit of f of x as x approaches c could equal f of c. Sometimes. Okay? When that happens, we say that f is continuous at x equals c. Okay? That's what it means for a function to be continuous at x equals c. It means the limit of the function as x approaches c is the same number you get when you plug in c. Okay? Okay, a couple more things. If f is continuous at every number in its domain, then f is called a continuous function. Okay? And one more definition. If f is continuous at every real number then f is called continuous everywhere. Okay, so there's our definitions for today. So let's look at a few pictures so you can get these ideas down, okay? I'm going to draw a few graphs. Well, let me highlight these words that we defined. Okay, so a few graphs to look at. Oops. Okay. Suppose we have a function that looks like this. Okay, let's look at that. Now I want you to notice something. That function is continuous everywhere except at x equals 2. But it is not continuous at x equals 2. If I asked you, why is f not continuous at x equals 2? What would your explanation be? There's only one correct explanation. Let me put some numbers on here. Let's say that's 5 right here. Let's say that's the point 2, 5. And let's say this is the point 2, 3, let's say. Okay. So why is f not continuous at x equals 2? There's only one reason. And the reason is f is not continuous at x equals 2 because the limit of f of x as x approaches 2 is what? It's 3. What is f of 2? F of 2 is 5, and 3 is not equal to 5. So the limit of f of x as x approaches 2 does not equal f of 2. That is the only reason we give for why f is not continuous at 2. Okay, it has nothing to do with drawing the graph without picking up your pencil. That has nothing to do with it. It's not continuous at 2 because the limit of f of x as x approaches 2 does not equal f of 2. Okay? Now, I'm going to erase that point. I'm going to change the function now. Okay? Now, I ask you the question. Is this function f continuous at 2? The answer is, it's a faulty question. It's neither continuous nor discontinuous. It's neither one. 2 is not in the domain of f. So the question of, is f continuous at 2, is not even a valid question to begin with. Okay, you see that? Now what about this? When I had that extra point up here, if I said, is f a continuous function? You would say, no, it's not continuous function because it's not continuous at 2. Okay? Let's take that point away. Now look at that function. And I ask you, is that a continuous function? The answer is yes. That function is now continuous, even though there's a hole in it. And here's the reason why. Where's the hole at? The hole's at 2. Is 2 in the domain of this function? No. All of the other numbers are in the domain of this function, and the function's continuous at all the other numbers. So this function now, the way it's drawn, is continuous at every number in its domain. So it is called a continuous function. Okay, and that has, again, nothing at all to do with whether or not you can graph it without picking up your pencil. Okay? All right. Let's write down some functions that we know are continuous. Okay. Polynomials. Those are always continuous. Rational functions. Those are continuous. Trig functions. Those are continuous. Okay? So if I was to ask you a question now, if I said, what's the limit of 5x squared plus 3x plus 2 as x approaches 1? Okay, if I asked you to do that, remember that earlier in the semester I said you do not plug in 1. You plug in numbers that are getting close to 1. Okay, but now we're in a different position. Now we've learned more. Now we've learned that polynomials are continuous, and that's a polynomial. So now you know that if you want to find that limit as x approaches 1, you in fact can plug in 1. Because why? Because it's a polynomial, so it's continuous. So the limit as x approaches 1 equals f of 1. And you're going to get 10 as the answer. You see how that makes finding the limit much easier? Okay. Now I want to look at 3 ways where a discontinuity can occur. Okay. So these are 3 common types of discontinuities. Okay, so here's one way that you could have a discontinuity. I actually already showed you this. I'm just repeating here. Okay, something like this. Okay, let's just call this C this time. All right. So this is where the limit of f of x as x approaches C exists but equals something other than f of C. So f of C and the limit of f as x approaches C are 2 different numbers. Okay, that is called a removable discontinuity. Not because you can remove the discontinuity, it's just that that's just what it's called. If you could move that point, you see, if I could take that point and move it right there, then the discontinuity would disappear. That's why it's called a removable discontinuity. But you can't actually move that point, though. Okay? All right. Another type of discontinuity is this kind. Where the limit of f of x as x approaches C doesn't exist because the left-hand limit and the right-hand limit disagree. So that would be a case like this. Okay? That's called a jump discontinuity. Now, just for the case of, I forgot the phrase. I just want to point out something again to you. If I removed that solid point and I did this, then that would no longer be a discontinuity. Why? Because C would no longer be in the domain of the function. So the function is neither continuous nor discontinuous at C. But if I fill one of those 2 points in, now C is in the domain, and the right and left-hand limits at C disagree. So there is no two-sided limit at C, and that's called a jump discontinuity. Okay? And the third common type of discontinuity we're going to call infinite discontinuity. Which is where one or both of the left or right hand limit is infinite. So something like this. That's called an infinite discontinuity. Okay? But again, only if C is actually in the domain. If you look at a rational function, here, let's look at this. You can rewind the video and look at those pictures some more if you want. Let's look for a minute at this. What about a rational function that does this? Let's say that here's the number 5. And what about a rational function that does this? So, what function would look like that? Maybe something like this. F of x equals the absolute value of 1 over x minus 5. Okay? Now, sometimes there's confusion here because some students will say, well, that's a rational function, so it's continuous. And other students will look at that and say, but there's an infinite discontinuity at 5. So who's correct? Well, the first student is correct. There's not a discontinuity at 5. So why is the second student wrong when they say, but there's a infinite discontinuity at 5? The reason that student's wrong is this, and this is like the third or fourth time that we're going over this. There's not a discontinuity at 5 because 5 is not in the domain. Okay? So that's not a discontinuity. And rational functions are continuous. Now, if I made a new function that looked like that, except also, like what if I did this here? So that, oh, I need to move this over so you can see it. There we go. if x is not 5 and f of x equals 1 if x is 5. Well, that's no longer a rational function. Now it's more complicated than a rational function. And then it would look like this. And that would be discontinuous at 5. And it would have an infinite discontinuity at 5. Okay? And there's a list of theorems that are very straightforward on page what is this page here? Let me see. Page 63 in the book. I'm going to show it to you. Okay, this is from page 63, Theorem 10. What does it say? It says that if you add or subtract two continuous functions, you'll get a continuous function. If you multiply a continuous function times a constant, it'll still be continuous. The product of two continuous functions is still continuous. And so is the quotient, as long as the denominator is not 0. And then a power or root of a continuous function is continuous. Okay, so those are good to remember. So if I gave you a function that was a polynomial plus a rational function, and I said, is that continuous? You would automatically know it is, because polynomials are continuous, and rational functions are continuous. And so their sum would be continuous. Okay. And there's one that's not written there, and I'm going to add to it. Let's call it number 7, which is composition. And that would be f of g. Composition of two continuous functions is continuous. Okay, that's all for today.